Good morning, everybody. I'm going to go over a few choice problems from the homework set to highlight some things that I think are important and might not be obvious to you from the work that we did in class. So I'm going to try to do parts of numbers 2, 4, and I believe 6. I don't know why I didn't space them the way I did, but they are what they are. So we're going to focus on this idea of a magnetic force due to a current or moving charges that are cutting through a magnetic field at some angle. Optimally, the angle is 90 degrees, but we also have to understand when it's not 90 degrees, and not only to understand the magnitude of the force, but also the subsequent motion, which is a nice application. So I'm going to go right to number 2. And this is something we kind of talked about in class with the E&M apparatus I showed you in class. So I have some magnetic field indicated with these downward lines, and then I have some particle. In fact, I believe it's an electron that moves to the left. And the first question, what's the magnitude and direction of the force? I think you can do that, so I'm not going to go over that right now. I want to really focus on B and D. So it says describe the path the particle takes as it moves through the B field and give any relevant measurements. And so it's just this part that I want to make sure we're clear on. I already demonstrated this in class, that as the particle moves perpendicular to the magnetic field, it's always going to feel a sideways force. And as long as it stays in a magnetic field, and we're going to assume that in this problem, even though the last line on the left is right here, we're going to assume it extends to the left and above and below indefinitely. We know it's going to move in a circle. So when I say give any relevant measurements, what I want to say is I want the radius of the circle. Okay, so you can describe the path. We've seen that in class. All right, so give the equation, derive the equation, because that's going to be important later on, for that circle in terms of what is given. So what do we know what's given? And then you can put the numbers in later. We know Q, all right? So if it's electron, we automatically know Q. We know B, the strength of the field, and we have V. Okay, so you can certainly find the radius of that. And basically what you're doing is a second law of motion. You have a force, that force is perpendicular, so you're going to get centripetal acceleration. And you can apply it appropriately. So I don't think you'll struggle with that. So let's say instead the electron moves at some angle 60 degrees. Okay, so from this diagram, it's not immediately obvious what the 60 degree is. So let me draw that in. All right, so right here, it's going to be kind of tight. That's my 60 degree angle. I'm not going to write in 60 degrees there because I just don't have enough space. So we asked 3 questions from this. What would be the force in the y direction? What about the x direction? And then what would be the subsequent path of the electron? So I'm just going to set this up. I'm not going to solve it for you. I'm confident that you can figure this out. So let me, actually, no, I won't do that. Let me take this velocity vector and just expand it right there. Okay, so there's our velocity. Here is one of the magnetic field lines. Here's our 60 degree angle. What you want to do, and I hope you recognize, is we're going to take that and the velocity vector and break it up into components, right? So in other words, some of it is, you could call it Vx, and the rest right here is Vy. And so as you answer 1 and 2, consider what the direction of each component is relative to the magnetic field. That's important. The general equation for the overall force, which I'm not asking for here, if you recall, is just QVB sine theta. Okay, so if you put in sine 60 in the Q, V, and B, you'll get the answer for the overall force. But I want you to understand this in terms of the components, because that's going to go directly towards the subsequent motion. In the problem above, right, it was since the electron entered perpendicularly, it went in a circle. Because it enters at an angle, and we have 2 different velocity components which interact with the magnetic field differently, you're going to get a slightly different path. So I want you to see if you can figure out what that path would be. And if you don't get it right, that's fine, but I think the answers should make it clear in hindsight, and we can talk more about that in class. Okay, so let me move on to the next problem. So I'm going to jump to number 4, and again, I'm not going to do the whole problem. but there's a very important lesson in part of it. So you might want to put a star or two next to this because this is a kind of a common problem where you have parallel wires where there's current in it. So I'm going to write IA in this one and IB in this one. Okay, and what besides the fact they're parallel wires of current going through them, the current is in the same direction. You could be asked questions where they're in opposite direction. You could be asked questions where there's a third parallel wire that might be with the others or in the opposite direction. So you want to understand the general gist of this. So the first question is, what is a net B field intensity halfway between the wires? So you've done problems like that before, and there's variations of that throughout this homework. So if I choose a point halfway, I basically got a B, right? So if I got a magnetic field surrounding this wire, okay, and if you use the right-hand rule, all right, I don't mind doing this much. You can see to the right of that wire, it's into the page, and to the left, it's out of the page. Okay, then if I do the same thing with the wire on the right, B, and again I apply the right-hand rule, I will see I have dots on the left and X's on the right. So it's not too hard to figure out what to do for the magnetic field intensity halfway between. You have an equation for that, and so I'll let you work that out. Well, hold on, make sure we have something. Yeah, okay. So the next question is what, and it's part B, that's actually the most common type of question. What is the direction the force A feels due to B? So F of A due to B. And so this is where things get kind of confusing because you got two different currents, you have two different magnetic fields, yet you have one force. So let me just point out that the reason A feels a force is because its current in A is cutting through B's magnetic field. Now I've only drawn the dots and X's just to the left of it, but those dots, right, keep extending out, and they get further and further apart per unit distance, all right, to the left, and then of course the X's extend to the right. So I want you to recognize that current of A cuts through B's magnetic field. A cannot cut through its own magnetic field. The wire in A, or wire A, cannot feel its own magnetic field, so it has to feel a field external to it. We could also argue that B feels a field or a force due to A's magnetic field. And so if you look at both of those using the third right-hand rule, you can see that they're consistent with each other, and then hopefully in hindsight it'll make sense why you get the answer that you do. Okay, so it's the last question that I really want to focus on. What must be the value of the current in both wires? So that was not given. Okay, but what you do know is you can set up an equation for the force one feels due to the other. So that force, let's say we'll take the force on A due to B. Okay, so if I set that up, we know that's a Bill equation. And since the wire is cutting perpendicular, I don't have to worry about the angle. So what I want to make clear is what B do we put in and what I do we put in. So I want the force on A due to B. So what that implies is that the magnetic field is coming from B, so I'm going to put a subscript there, right? I want the magnetic field due to B, but it's the current in A, right? Now I was talking about that earlier. A is cutting through B's field. And if I ask what's the force of B on A, I would reverse the subscripts here. Okay, so you can plug in the numbers and you will get an answer. It's an interesting answer. Now, I think we make clear the current is the same in both wires, so use that when you go to solve this general formula here. So you weren't given B of B, but if you go up to this problem, there is an equation that you can set up for the B of B and combine it here. Now I want you to understand how these parts fit together. When you come up with the answer, well, heck, I'll just tell you the answer, but you can prove it for yourself. You will find that I of A equals 1.0 amps. Okay, And that's not a coincidence. And there's a purpose why I want to do this. So we set up a 1 meter long, and really that 1 meter is not really relevant. As long as the wires are sufficiently long enough, it'll work out the same way. They're placed exactly 1 meter apart, and we feel a force of 2 times 10 to the negative 7th newtons. Again, that force is not a coincidence. It was by design for this problem. What this does is this situation allows us, when we have, okay, so let me step back a second. So if we set up this situation exactly as it is, where we set up 1 meter apart 2 wires that are sufficiently long, and if we measure a force that's as close as we can get to 2 times 10 to the negative 7th, then we know we have 1 amp. And this is how we define the ampere. So in physics, you have to, if you have a definition of a unit, you have to know how much you have of that unit, or how you know you have that much. It's not easy with electricity. You would think that the fundamental unit would be a coulomb, but it's impossible to know when you have exactly 1 coulomb of charge, because you can't count the charges. So what we have to define, what's easy to define because we can measure it, even if indirectly, is the ampere. So that is a fundamental unit of electricity and magnetism. So the coulomb, which you might think is a fundamental unit, is really divided as an amp times an amp second. Okay, so if you know you have exactly 1 ampere for 1 second, then you know you have 1 coulomb of charge that's passed through. The volt can also be defined in terms of an ampere, in terms of Ohm's law, or in terms of, probably more easily, in terms of power. So if a volt is voltage is power divided by current, right? And we could break that down, the power, into kilogram meters per second squared. So that's kilogram meters squared per second cubed. That's what power is, divided by an ampere, right? So that's the definition of a volt. Okay, and in a Tesla, we can do something similarly, right? That's a Newton meter, Newton per amp meter. And so we can define that and break the Newton down into fundamental units, etc. Okay, so again, this is how we know you have an ampere, is when you have 2 parallel wires that give a specific force for a specific separation distance, and then we know we have 1 amp. All right, I have a few minutes left. Let me jump to number 6. Let's see if I can fit that in. So I'm not going to solve this problem, but I'm going to set up certain parts. It's a really, really neat problem because it combines electric fields with magnetic fields for the first time here. There are values here, but actually all I'm interested in you doing is be able to solve for equations, do some simple derivations. So let me explain what this is. So suppose you have a pure material of unknown composition. It can usually be identified found by sending ions of the substance through a mass spectrometer. So this is a mass spec. It's important that the unknown particles be ionized because the charge on the particles allows the forces to be exerted on it by both electric fields and magnetic fields. So it's a really cool idea. So you have some source out here, okay, that has a voltage across it that's going to accelerate the particles into this chamber at some velocity v. Don't confuse that v with the voltage. And the idea is, if you set up the electric field, right, here's someone got some parallel plates, you can set it up and you have concurrently in there a magnetic field with the x's that's pointing perpendicular to the E field that's pointing into the page. You can set up a strength of E and B such that the particle moves through completely undeflected. So that's a hint for part A. If it's undeflected, then you can talk about forces. Then when it enters region 2, it's just the magnetic field, and since it comes in perpendicular to that magnetic field, it's going to feel a sideways force and move in a semicircle here. And what you can measure from that semicircle is the radius. And from that radius, and knowing something about the E field, which tells you something about the velocity, you can figure out what the mass of that object is, and thus its identity. So in question A, we want you to derive the equation for how fast this is moving in terms of E and B, with the idea that the forces are balanced. In B, we can ask you what sign must this particle be. So when it enters, so you can't figure that out from region 1, but you can figure it out in region 2 based on the way it deflects. So there's a nice third-hand rule application. You can go back once you figure out the charge, what direction the E field is, that's part C. And then in D, which is the most interesting part of this, is if you know the magnitude of the particle's charge is something Q, you can derive an equation for the mass in terms of the givens. And the givens are the B field intensity, the E field intensity, and Q. Okay, you can't use V in your final equation. You use the equation to derive up here.